Hello friends, we will continue our discussion on the problem of particle in one-dimensional box. You will recall that in the earlier session on particle in one-dimensional box, we started by recalling the wave mechanics, the formalism for understanding quantum mechanical systems in terms of the postulates and the strategy used for the purpose there. And thereafter, we formulated the Schrodinger wave equation for particle in one-dimensional box. Having defined the system, we formulated the Schrodinger wave equation, and thereafter we solved the equation for the three regions there, region 1, 2 and 3. 1 and 3 happens to be outside the box, whereas 2 happens to be the region within the box there. And then in the process we got the wave functions, and then we tried to imply the boundary conditions, and in the process we got wave functions which we formally normalized towards the end of it, and we could get normalized wave functions there. So that's where we stopped in the last session. We will continue from there, and the today's session, what we're basically going to do is that we will try to see that how do I formulate an energy expression for particle in one-dimensional box. We will pick up threads from what we did in the previous session, and then thereafter we will try to analyze what does this energy expression convey to us, and then we'll come down to a very important aspect of this problem of particle in one-dimensional box, that is how do I visualize the wave functions. That means the wave function which I got in the previous session, we will try to see that what do they convey to us. Then we will briefly touch upon what is called as a correspondence principle, and then we will try to sum up what we do in today's session. Okay, now as regards the energy expression, if you remember that in the previous session when we tried to solve Schrodinger wave equation for particle confined to the box, we made a substitution over there, and substitution happened to be that alpha square to be equal to 8 pi square h and so on and so forth over there. Let's look at the expression here. The expression is that we made the following substitution, that is alpha square to be equal to 8 pi square me by h square. That is the substitution we made, and then towards the end we get some expression in terms of the value of alpha, because by imposing the second boundary condition there, and that alpha came out to be plus minus n pi by a. Now we started by making this substitution, and also in the process of ensuring that is the wave function adheres to boundary condition, I get alpha to be equal to plus minus n pi by a. So what do I do now? What do I do now is I just square this term alpha here. If I square it, I get as n pi by a square, and equate it with what I substituted to make a beginning of solving the problem of Schrodinger wave equation for particle in one-dimensional box. When I do that, I find that n pi by a square to be equal to 8 pi square me by h square. What do? I just simplify it, rearrange the terms there, cancel the common terms over there. What I get is I get en, and just to put a qualifier over there, to be equal to n square h square by 8 ma square. That is a very crucial expression over there, because this tells me that is E, energy of the particle in one-dimensional box, is dependent on the following terms over there. H is a constant here, m is a constant, that's the mass of the particle, a is the length of the box, which again is constant. That means we defined it to be from 0 to a, so a is the dimension of the box there. So the only variable happens to be n here, and that n came from the expression over here. Okay, now what does it mean? And then we also know that n can take values of 1, 2, 3, 4 up to infinity. It can take any positive integer value there. Okay, what does it convey? It conveys to me that the energy happens to be quantized. That means energy can take up, say I want to put as n is equal to 1, so E1 will be equal to 1 square, that is 1, that is h square by 8 ma square. For n is equal to 2, it will be 4h square, and so on and so forth. For 3, it will be 9h square. And what you find is that is, since energy, the particle can take up only certain energies. It can take as h square by 8 ma square, or 4h square by 8ms square or 9 and so on and so forth. That means it can take up only certain energies. When it so happens, then we say energy is quantized. So what you find from here is, that is, the quantization is coming as a consequence of confinement. What does it mean? If you remember in the previous session, this term that alpha to be equal to n pi by a came when we imposed second boundary condition. That means when we wanted to ensure that the wave function adheres to the second boundary condition, we came across this particular term over there. That means this term n came as a consequence of imposing the boundary condition, or in other words, in simpler words, trying to ensure that the particle is confined to the box. That means the confinement of the particle in the box has led to its quantization over there. That the energy is quantized. Okay. Now let's go further and see what does this energy expression convey to us. Because keep this expression in mind that En to be equal to n square h square by 8ma square, where h is Planck's constant, 8 is a constant, we know that, m is the mass of the particle, a happens to be the dimension of the box over there. Okay. Now if I just look at this, so what you find is that energy happens to be directly proportional to n square, that means square of the quantum number n over there, and also it is inversely proportional to m, that is the mass of the particle, and a square, or a in other words, that is the dimension of the box over there. And one technical term over there, that is when n is equal to 1, that means when E is equal to h square by 8ma square, this energy is termed as 0 point energy. That means the minimum energy which the particle in one dimensional box can acquire. It cannot have any energy less than that. That is called as a 0 point energy, but it doesn't because n cannot be 0. If n is equal to 0, energy is 0. And when n is equal to 0, even wave function will be 0. The particle will not be able to exist there. So the requirement is that n happens to have a value of, as I mentioned before also, only positive integral values over there. Okay, it can be having values only of 1, 2, 3 up to infinity. And when n is equal to 1, that happens to be that E1 to be equal to h square by 8ma square, and that is called as the 0 point energy of particle in one dimensional box. Okay, let's go further and see that how does the energy level diagram look like. Say for n is equal to 1, this happens to be h square by 8ma square. For 2, it is 4h square by 8ma square. For 3, it is 9. This basically, it is increasing as a square of n. So this is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, and so on and so forth. You can see that at n increases, the energy level is getting farther and farther. Energy increases very as a function of square of the quantum number over there. That is a very simple thing, straightforward thing. That is, there is a direct proportionality between the energy and the square of the quantum number over n over there. Okay, that is one aspect of it. Let's go further and see that if I just try to see the difference in energy levels over there. Say, I have this energy level 1, energy level 2. So one is h square by 8ma square. This is 4 times that. This is 9 times that. If I look at the difference between the two, so from 1 to 2, the difference happens to be 3. From this to this happens to be 5. From here it is 7, and so on and so forth. The delta E value, that is the difference between a given energy level and the next one, goes on increasing as n increases there. Let's see it mathematically. If I try to find out the delta E for n plus 1 square minus n square h square by 8ma square. That means this is n plus 1th level, this is nth level over there. If I do that, I find that the expression comes out to be 2n plus 1 h square by 8ma square. Say for n is equal to 1. So if this comes out to be 3h square by 8ma square, it means when n is equal to 1 means the level 1 and 2, the difference happens to be 3 times that, 3h square by 8ma square. And if n happens to be 2, this will be 5. If it happens to be 3, it will be 7, and so on and so forth. Now, another thing which you have to see here is that this delta E value is proportional inversely to m and a square. Now, suppose let's focus attention onto the mass of the particle. Larger the mass, closer the energy levels there. Suppose if I just take the same box but increase the size of the particle over there, mass of the particle, what will happen? If the mass of particle increases, this delta E value will get smaller and smaller. That means levels will get closer and closer. And if mass happens to be very large, it becomes a classical particle. Say, I think of a cricket ball. It's a classical particle. It's not quantum mechanical system. If the mass is so very large, we find that the delta E becomes close to zero. Or in other words, we say the energy happens to be continuous. It's not quantized. And then we see that quantization is a concept which is valid only for systems which are microscopic in dimension. I mean, very, very tiny sizes and the dimensions over there. Okay. So that actually comes from this expression also. That is, if m becomes large, the system starts behaving classically. That means the delta E value comes very, very close to zero there. Okay. Now let's go further and see one more thing over here. Same thing. If I look at the size of the box now, size of the box, we see the expression is the same what we had in the previous slide over there. So you see that if A increases, let's understand what does it mean. What we find is that this delta E is proportional inversely to 1 by A square. A happens to be the size of the box over there, that dimension of the box. Now suppose I start increasing value of A. That means this was 0 to A earlier. Now if I go on increasing the length of the box, what will happen? As length of the box is increasing, delta E goes on decreasing. And if I go on increasing, I make it infinite. If I make the A to be infinite, what will happen? Delta E will become zero. That means there is no differentiation, there is no quantization left now. Energy becomes continuous again. And we know that if we have a particle which is a free particle, suppose there is no confinement of any kind, we know that the energy of free particle is not quantized. That also comes from this expression over here. That is, the quantization is only possible when there is a confinement. Okay. I'm trying to stress it again and again because the free particle doesn't have quantization of energy over there. Now let's move further and talk about the significance or the meaning of the wave function what we got in the previous session. And to understand that, let's begin with the very first wave function, that is when n is equal to 1. That means the ground state wave function there. Let's look at the expression. Say for n is equal to 1, we find that our psi will be equal to root 2 by a sine of pi by ax. That is because n is equal, because the expression we had was n pi by a. So I put n is equal to 1, it becomes pi a by x there. Now what do I do next is, I take different values of x. So say when x is equal to 0, this whole thing will be equal to 0. If I take x equal to a by 8, that is just put it a by 8, a will cancel out, it will be psi pi by 8, that is 0.382. If I go on taking different values of x, and I find, I just draw a small table over there, and then what do I do next is, I make a graph of this. That means on the y-axis, I have got wave function that is psi divided by root 2 by a, and on an x-axis, this is my 0 to a, that is the box over there. When I plot this graph, what do I find is, the graph looks something like this. That means at x is equal to 0, the wave function happens to be 0. X is equal to a, wave function happens to be 0 again. That is what we showed earlier too, because since at 0 and a, the potential happens to be infinite, the wave function must go to 0. But what we find is that the wave function happens to increase from the boundaries and comes to a maxima in the middle of the box there, which is very, very intriguing. It is a very strange behavior. And this behavior is very contrary to what we expect classically. We'll come to that too. So this is as regards the wave function for particle in one-dimensional box for n is equal to 1. That means the ground state wave functions looks something like this. Let's move further and see what happens if I try to look at other wave functions for different values of n over there. Say for n is equal to 1, wave function looks like this. If I do the same exercise as we did for n is equal to 1, for say n is equal to 2, wave function comes something like this. It is 0 to begin with, becomes a maxima at about a by 4, and then comes to 0, becomes negative, becomes minimum, and that starts increasing, comes to 0 again. For n is equal to 3, maxima, minima, maxima, and so on and so forth. We find that the wave functions have got peaks and troughs. There are certain maxima, certain minimas there. And some of the peaks and troughs happen to be equal to n. Say for n is equal to 1, there is only one peak. For n is equal to 2, there is one maxima, one minima. For n is equal to 3, there is two maxima and there is one minima. For n is equal to 4, two maxima, two minima, and so on and so forth. And then what you find is that these are different, but as I've been saying again and again, these do not have a physical significance by itself. That's the basic premise of our wave mechanics. That is, psi doesn't have a physical significance of its own. We can't read much into that, but the square of psi gives me some measure of the probability. So let's try to look at now, if I take the square of wave function, what do I get? Let's have a look at it. When I plot the square of wave function now, this is my psi square. So what do I get here is that, say for n is equal to 1, I get a similar graph as before. But now only thing is, since it was a smaller fractional number, the square of that becomes still smaller. So the height of this happens to be slightly less. But nonetheless, the probability, because now it's referring to probabilities, happens to be close to at 0, and at A the probability happens to be 0 and happens to be maximum in the center of the box. That's what it is. For n is equal to 2, there is a maxima here at A by 4 and 3A by 4. For n is equal to 3, there are 3 maximas there at A by 6, at 3A by 6 and 5A by 6. For n is equal to 4, there are 4 maximas. So we see that in case of psi, we had maximas and minimas. That's a wave function. It's an amplitude function as it varies. But if I take the square of it, wherever there was a minima, the square of that also will become a maxima, because negative square becomes positive there. So there will be maximas only. So what's very interesting observation we have here is, say when n is equal to 1, there is only one maxima. For 2, there are 2 maxima. For 3, there are 3 of them. For 4, 4 and so on and so forth. So if I go on increasing my quantum number n, say for n is equal to 50 or 100, there will be 100 maximas over there. Okay, so that is the implication what I'm getting over there, and we will see a very, very important consequence of that particular thing here. That is, the number of maximas is equal to the quantum number over there. We'll just come to that very, very soon. But before that, let's have a look at one more aspect of it. If I look at the wave function, say n is equal to 1 is fine. Say look at n is equal to 2. So what do I find is, say for n is equal to 2, when at 0, the wave function, the square of wave function, that's the probability or probability density for that matter, happens to be 0. But it becomes maximum at A by 4. But at A by 2, that is in the middle of the box, the probability happens to be 0. And then again a maxima at A by 4, and then at A it happens to be 0 again. So what's interesting here is that at this point, that is at A by 2, in the middle of the box, there is a 0 probability of finding particles. Probability happens to be 0 at the boundaries, increases, come to maximas at A by 4 and 3A by 4, but at the center of the box, the probability happens to be 0, which is very strange. But this actually, this is what's called as a node, a region of 0 probability, so to say. But this should not be 0. This should be actually a positive number, but a very, very small positive number over there. The probability is not 0. It is finite, but very, very close to 0. So essentially, the point I want to bring home is that when n is equal to 2, we find that there is a region in the middle of the box where the probability of finding particle happens to be 0 or very, very close to 0. For n is equal to 3, if I go, I find there are 2 such places there. That means there are 2 places where there are nodes over there, regions of almost 0 probability. For n is equal to 4, there are 3, and so on and so forth. So there are n minus 1 nodes in the wave function's square plotted as a function of the distance of the x dimension over there. Okay, now let's go further and look at one more aspect over there. Suppose I'm talking about a particle, a classical particle there. If I'm looking at a classical particle, suppose I have just think of a box, an ordinary, maybe a shoe box over there, and there is a small ball over there. If I make it move within the box, I find that the probability of finding this particle will be same throughout. There is no reason for the particle to be more likely to be in the center or in the corner or somewhere else, because classically speaking, I would expect the particle has got same probability to be found at any place in the box over there. That is, I can show that do something like this. Whereas in quantum mechanical system, where you just saw that the behavior of quantum mechanical system, that is a particle in one-dimensional box, is very different. Say for n is equal to 1 level, the probability is maximum at A by 2. For n is equal to 2, it is different, 3, and so on and so forth. And if I look at, say, a system, say when n is equal to 100, I will have 100 maximas over there. And if I just try to see, if I just join all the maximas over there, I find that this is somewhat similar to what we had in the case of a classical system over there. And that is exactly what happens there. That means for very large values of n, the quantum mechanical behavior starts becoming classical behavior. And this is what is called as correspondence principle over there. Okay. Now, let's try to sum up what we've done in this session. What basically we've done is we continued from our earlier session on particle in one-dimensional box, and we started by working out an expression for energy, and that energy expression came out to be that En to be equal to n square h square by 8ma square, where n happens to be a quantum number whose values can be 1, 2, 3 up to infinity, which actually showed that energy happens to be quantized. That's one bit. And thereafter, we try to analyze this expression. We found that the energy is directly proportional to the square of the quantum number, 1. Secondly, it is inversely related to the mass of the particle and also the dimension of the box. Also, we analyzed it and found that if the mass of the particle becomes large, then the delta E value, the difference in energies of the kind of consecutive energy level gets very, very close. That means at very large values of mass, the quantization is lost. Similarly, for very large dimensions of the box, again the quantization is lost. In other words, we say a free particle is, the energy is not quantized over there. Having analyzed the energy expression, we came down to looking at visualizing the wave function, and we found that for different values of n, we take a wave function and then try to plot a graph between the distance or the x-axis as the location of the particle in the box, and on the y-axis the wave function part of it. We found that the wave function is different. There are maximas and minimas over there. For n is equal to 1, there is a maxima in the middle of the box over there. And when we went on further, we talked about the probability. The probability, as per the fourth postulate we mentioned earlier, is given by the square of the wave function. Then what we did was we plotted the square of wave function, and then we found that the square of wave functions had maximas only. For n is equal to 1, there was one maxima. For n is equal to 2, there were 2. For 3, there are 3, and so on and so forth. And then for a very large value of n, we find that there will be as many maximas as is the quantum number there. Thereafter, we touched upon one more very interesting and intriguing aspect of quantum mechanical behavior, that is the existence of nodes there. Say for n is equal to 2 level, we found that the probability of finding the particle is maximum at a by 4 and 3a by 4, but 0 at a by 2, and that is actually we refer to as node. For n is equal to 3 level, there were 2 such nodes, and so on and so forth. There are n minus 1 nodes for a given energy level characterized by different quantum number, n is equal to 1, 2, 3, and so on and so forth. Then towards the end, we touched upon what's called as a correspondence principle. Say for n is equal to 100, there will be 100 maximas, and if I join all the maximas there, this becomes somewhat similar to what we have in case of classical particle. With that, we complete our discussion on particle in one-dimensional box. In next session, we will talk about particles confined to a larger box, maybe a 3-dimensional box over there. Thank you.